Hello, this is Mahendra Didia. This is the second related video on physicochemical characterization of suspension. This submodule is part of the book on liquid formulation that utilizes Qubit's video book format. In this particular submodule, we will look at sedimentation of solids. Suspension contains particles dispersed throughout the liquid phase in which the particles are not soluble. Sedimentation of solid will occur due to gravitational force. The factors that influence sedimentation include density. The particle will sediment in a fluid if its density is greater than the fluid in which it is suspended. It will float if the density is lower. Particle size range. Different settling rates between large and small particle will change effective density of suspension. And you saw the video in the previous submodule on settlement of particle size of different ranges. Concentration of particles. There's an interaction between particles as they settle. And there's an increase of frictional force at the surface of the settling particles. We'll see in this video some of these effects. Different particle size, red, blue, and yellow, settle at different rate. And this is called free settling. They are not interfering with each other depending on their radius. If the concentration goes above 1%, there will be an interference. As it can be seen in this graph, the sedimentation can be graphed as a factor of time. And this is classical hindered settling. And this is most common in most suspension. The graph of clear liquid on top and the height of sediment versus time gives information on how suspensions are behaving. So the rate declines, and at any given time we can look at supernatant, original concentration of suspension, variable concentration, and sediment is very critical in understanding of suspension stability. Here's a suspension. This is demonstration, so it's settling much faster than normal suspension would settle, but you can very clearly see the supernatant. And now we can start seeing bottom where the sedimentation is. So all different zones can be seen in this kind of suspension. And this figure shows the different types of suspension and different settling. Different formulations will behave differently. Rate of sedimentation of solids. We will see an example video and theoretical explanation. In this case, we will see glycerin and water. Glycerin has a viscosity of 0.95 Pascal per second. Water is 0.001 or 0.01 centipoise. Glycerin density is 1.26, whereas water is 1 gram per cc. We will see a solid particle settling in water very rapidly. In slow motion, this is for the demonstration purposes. In glycerin, same particle sediments at very slow rate. This is due to glycerin's density and glycerin's viscosity, which are higher than water. The rate of sedimentation of solid is described by Stokes' equation. Stokes' equation on physicochemical properties affecting sedimentation, velocity, distance over time, is valid for dilute suspension and spherical particle. However, it is widely used as a first estimate of suspensions. Velocity is proportional to the diameter square, density difference, and gravitational force divided by 18 times the viscosity. The diameter of the particle plays an important role. Smaller the diameter, less is the velocity. Densities can be adjusted by formulations. Viscosity of the suspension is extremely important, and that can be adjusted by formulation. In the next slide, we will see that on the velocity. We saw the video a few seconds ago. Now we will see velocity differences are. This is rate of sedimentation of a drug particles from an oral suspension. Average diameter of the particle D50 is 1.9 micron. It's a micronized material. 1 micron is equal to 1 divided by 10,000 centimeter. Convert every unit into cm, centimeter, or cubic centimeter. Density of particle is 1.4. Density of medium, in this case water, is 1.0 grams per cc. Gravitational force is 980 cm square. And viscosity of medium is 1 centipoise. Convert that into 0.01 gram per centimeter second. That's the viscosity of water. Take Stokes' equation and enter these values, and we get a velocity of 7.86 10 to minus cm per second. This is difficult to read. We converted 0.283 centimeter per hour, and velocity is 25 meters per year, that means drug will settle very fast in water. Take glycerin alone, velocity to 4.95 times 10 to minus 8, which is 0.0001 centimeter per hour. We convert that into 0.9 centimeter per year. Glycerin reduces particles sedimentation rate. Suspension can be redispersed if they are flocculated. If they are deflocculated, they are difficult to redisperse. Dispersibility is capability of suspended particle in the continuous phase in the suspension to return back to its original particle size, shape, and distribution. And dispersibility ratio, dr, is the theoretical diameter of a dispersion that's acceptable versus diameter that's measured at any given time. In the next portion of the slide, we look at milk powder, called growing up milk powder. There are two products. This is flocculated, no individual particle. In this case, there are many individual particles shown by the arrows. Significant number of particles are individual. Thermal analysis will be different. It will show unencapsulated the fat, and that's what this peak is showing. When we resuspend it, redisperse it, deflocculated system here show lump formation. Deflocculated with smaller particles show lumps, whereas flocculated systems do not show lumps with gentle agitation. Solid redispersibility is extremely critical in pharmaceutical preparations. Many pharmaceutical preparations are flocculated systems. Well, sediment, and it's a thermodynamic process as explained by Stokes' law. Sedimentation is reversible for flocculated system. Redispersion criteria are based on dispersibility ratio. Upon shaking of a container, it needs to return back to its original particle size and distribution. For pharmaceuticals, proper instruction must be provided to the end user, such as shaking, stirring, mixing, etc. Pharmaceutical labeling for suspension includes that. shown here for naproxen oral suspension, 125 milligram per 5 ml. It clearly states shake well before using. In addition to that, pharmacists will provide attached medication guide to each patient. Suspension is a biphasic heterogeneous system. There are two different phases. Solid phase should be uniformly distributed in order to assure uniform dosing. Suspension will come in the bottles like this. You cannot see inside whether the suspension has settled or it is homogeneously distributed. If suspension is distributed uniformly, micropicture of them look like that. If it's aggregated, what suspension would look like, we will get non-uniform drug dosing. FDA is very concerned about for suspension. They have a clear guidance on suspension and quality control of it. It clearly states that suspensions are unstable and they will segregate under the gravitational force. Stokes' law also tells us that viscosity of suspension is very critical. If the product does not have appropriate viscosity, then segregation will occur in the bulk storage conditions, filling equipment, and in the bottle itself. It will provide non-uniform dosing. So FDA guidance on GMP, good manufacturing practices, warrants that testing of bottles from beginning, middle, and end to assure no segregation has occurred during the manufacturing and packaging. In many cases, it requires in-process testing of suspension, including assays from the bulk tank, from several locations, and viscosity testing. Sedimentation of a solid, dose uniformity case study in FDA. Carbamazepine is an oral suspension used to treat seizure. Patient prescription in this case called for 8-ounce bottle of carbamazepine. Because medication in this case came in 16-ounce, smaller bottles were prepared by pharmacy at each refill. It was noticed by the end user patient that suspension had different visual appearance from a previous prescription. So end user complained and sent several suspicious looking suspension bottles to the manufacturer. Manufacturer found that 3 of the bottles contained suspension that had less concentration than expected, and 1 bottle was super potent. 3 times investigation occurred, and it was concluded that the pharmacy staff member that was dispensing from a 16-ounce bottle into 8-ounce bottle did not shake well the 16-ounce bottle before dispensing into 8-ounce. This is a real occurrence that happened several years ago.